All right, so we're going to prove homework 7, problem number 3. It's theorem 5.3, which says that the order of a permutation of a finite set written in disjoint cycle form is going to be the least common multiple of the length of the cycles. All right, so we're going to start out by saying that a cycle of length n has order n, right? And we're going to let alpha 1 and alpha 2 be disjoint cycles of length m and n. And we're going to let the least common multiple of those two numbers equal k. So based on theorem 4.1, alpha 1 to the k is the identity, because if alpha 1 to the n is the identity, right, and n goes into k, that means that alpha 1 to the k is the identity. We can also say the same about alpha 2. So based on theorem 5.2, we know that disjoint cycles commute. So we can rewrite this as alpha 1, alpha 2 to the k equals alpha 1 to the k, alpha 2 to the k, which is e times e, which is e. Now, theorem 4.2, corollary 2, if a to the k equals e, that implies that the order of a divides k. So we're going to use that to show a very important thing, that the order of alpha 1, alpha 2 divides k. And if we let the order of alpha 1, alpha 2 equal t, that would mean that t divides k. Now, if we can show that k divides t, that would have to mean that they are equivalent to each other. So we'll do that next. So alpha 1, alpha 2 to the t can be rewritten as alpha 1 to the t, alpha 2 to the t. And we already know that that's the identity. And if we multiply from the right by alpha 2 to the inverse t, we're going to get a cancellation here. And we're going to end up with alpha 1 equals alpha 2 to the inverse t. Now, alpha 1 and alpha 2 are disjoint cycles. They share no common elements. Okay, so that's going to imply that alpha 1 to the t, alpha 2 to the inverse t are also disjoint cycles. So since we proved that they are equal to each other in disjoint cycles, they must both be the identity. Okay, so that's going to imply that m divides t as well as n divides t. And so that would mean that their least common multiple, k, is also going to divide t. And if t divides k and k divides t, then k equals t. So therefore, we can say what we're trying to prove, that the order of alpha is going to be the least common multiple of its parts.